So our next section that we're going to talk about is the mean value theorem. And before we talk about the mean value theorem, we're going to talk about Rolle's theorem, because Rolle's theorem is essential in the development of the mean value theorem. And so what Rolle's theorem says is that if we have a continuous function on a closed interval, and you'll notice that almost all of our definitions say that, and we can find the derivative everywhere on the interior of that function, if there are two y values that are equal, then there's at least one critical number c on that interval for which the derivative is equal to 0. So, all Rolle's theorem says is that a differentiable curve has at least one horizontal tangent line between any 2 points where it crosses a horizontal line. It may have just one, but it could have more, and you'll see these two pictures. So, visually again, I'll show you. Suppose I have a curve, and if I draw a horizontal line through it on some interval, say we're just considering A and B, so I'll erase that part of the curve and this part of the curve. Essentially, if I can draw a horizontal line through the curve and we have two y values are the same, then we know somewhere in between on that interval between A and B, there's going to be somewhere else that has a horizontal tangent line. And in this situation, there are two places. So there's going to be at least one max or min. So if you can draw a horizontal line through a function and it crosses that function at 2 points, then somewhere between those 2 points, there's going to be somewhere else where you can draw a horizontal tangent line, which would represent a max or min. So we're going to do an example here. We're going to show that this equation has exactly one real solution. So we're dealing with the equation x cubed plus 3x plus 1. So in order for us to do this, we're going to have to show a few things. The first thing we'll do is we will define this. We're going to call it a function. So we've got f of x equals x cubed plus 3x plus 1. All right? And so the first thing I'm going to show is that it has at least one solution, not exactly. So, but the intermediate value theorem says, says that if I plug in two different x values and one is negative and one is positive, I know there exists at least 1 0 between those values. And we can choose any two values we want. In this situation, I might plug -1 into the function. That gives me an output of -3. And I could plug 0 into my function, which gives me an output of 1. And since one of these outputs is negative and one of them is positive, so we'll think about one being below the x-axis and one being above the x-axis, we know that the graph is going to cross the x-axis at least once because it had to go from being negative to positive. Now, it could cross a whole bunch of times, right? But it only has to cross at least once. So we know that a solution to this function exists. When I say solution, I'm saying that there's a 0. So we know there is at least one point where this graph is going to cross the x-axis. But say there was a possibility that we could have two. So we maybe have 2 points, x equals A, x equals B. And so we're thinking, hey, these 2 points are both zeros. Well, if they are both zeros, then they would both have y be equal to 0, right? So there would be 2 spots where f of x was 0. And Rolle's theorem would then say, well, if we have two y values that are the same and they're both equal to 0, that somewhere between x equals A and x equals B, there would have to be another point that would represent a max or a min, which would say we've changed from increasing to decreasing. There'd be a turning point. All right? So, if we think about our derivative, f prime of x equals 3x squared plus 3. So, if there was a horizontal tangent line, the derivative would need to equal 0. And this is a quadratic function that is above the x-axis. It's never equal to 0. It's always positive. And so because the derivative shows that we don't have a max or a min, we know that our function is always increasing. It's always going from less than, below the x-axis, to greater than, above the x-axis. All right, and the main use of Rolle's theorem is to prove the mean value theorem. And so Rolle's theorem dealt with horizontal lines where you would have two y values that were exactly the same. And the mean value theorem, which was stated by Lagrange, is a slanted version of Rolle's theorem. And basically, the mean value theorem guarantees that there is a point where the tangent line is parallel to the secant line joining two values. Okay, so on the left here, we have the equation for slope of a secant line, and we're saying, well, the secant line is going to be equal to the slope of the tangent line, the derivative, at some point C, which exists between A and B. So, mean value theorem, suppose we have a function, continuous, closed interval, differentiable, then there's one value between A and B in which the secant line has the same slope as the tangent line at some point C. And so we're going to prove this. We're going to think about some curve. We're going to consider this here. Let me draw a little curve. And we might have some point A, which I will call A f of A, or rather just capital A. And then some value B, B f of B. Okay, and so what the mean value theorem was saying was that if I can draw a secant line somewhere between those 2 points, A and B, there would exist a tangent line that has the exact same slope, and it'll always be true. So we're dealing with these 2 points, A and B, and so we're going to define the graph of the secant line, and we're going to call the secant line graph g of x. So normally when we write the equation of a line, we use y equals mx plus b. Okay? So in this situation, I'm going to say a y, I'm going to call it g of x, equals f of a, some y value where x equals a, plus our slope, f of b, minus f of a over b minus a times my x, which is a units away. When I'm talking about g of x here, I'm talking about this secant line. So I'm basically forming a way to write that equation using my curve f of x. And so f of x is this curve that we're dealing with here. And the vertical difference between the graphs of f, the curve, and g, the secant line, could be defined as h of x equals f of x minus g of x. Or we can say h equals f of x minus that part of the function we'd written up there for the secant line, f of a plus f of b minus f of a over b minus a times, and I'm running out of space, x minus a. And the function h satisfies the hypotheses of Rolle's theorem on the closed interval AB. It's continuous on the interval and then differentiable on the open interval AB because both f and g are. Also, what we can say, h of A equals h of B equals 0 because the graphs of f and g both pass through A and B. So therefore, C, somewhere between there, h prime of C is going to equal 0 at some point as long as C is on that open interval between A and B. So now I'm going to differentiate this. I'm going to verify this by taking the derivative of h. So we could say h prime of x. The derivative of f of x would be f prime of x. Derivative of f of A is 0, so plus 0, we don't need to write that, plus the derivative of slope. Well, slope is just a value, so that's a number. So this last term here, we've got some number times x minus a number. Or rather, some number times x minus 4. That might make it easier to explain. So if I distributed this, I would say that number, x, my slope, minus 4 times that number. And the derivative of this would just be that coefficient there in the front. And that number I'm talking about was the slope. So it does turn negative. And that is my fault because I didn't distribute that up here. So that negative goes there. And we end up with f prime of x minus f of b minus f of a over b minus a. So if we took this derivative, h prime of x, and we evaluate it at c, that gives me f prime of c minus f of b minus f of a over b minus a. And if we set this derivative h equal to 0 to try and solve, and that lets us know if we have a max or min in between. So setting it equal to 0, we've got f prime of c equals f of b, minus f of b minus f of a over b minus a. We can see here, using algebra to move the terms around, that we end up with f of b minus f of a divided by b minus a equals f prime of c, which that is our mean value theorem. So basically we developed the mean value theorem. That's what we set out to prove.